Hello and welcome to section 4.1 Antiderivatives, and in this section we are going to be basically working backwards from a derivative function. So we're going to have a velocity function and we're going to work backwards to find position functions as we work through this. And so first one here is they want a general solution. We'll talk a little bit more about what a general solution means of this function. And so we're saying the derivative is 2, and so that meant that I took some value, and when I took the derivative I got only 2 left over. So if I do the antiderivative, I'm going to say, well, it probably had a value of x, because remember the power is 1 multiplied by the power reduced to 0, and so I was left with 2. And so that would be my antiderivative of this. But the problem is, how do I know that the y-intercept is 0? Well, I don't know what the y-intercept is, so I have to represent some new y-intercept in this case, which would be some constant. So we're going to call it a constant of c. And we don't really care what that number is unless they ask us for it. In this case, this is what we're looking for. And when you see when they ask for a general solution, they're talking about this function with a c in it. And this ends up giving us a family of functions that basically would represent, if I took the derivative of this, I would get back to what I started with here, that y prime was 2. A family of functions with a slope of 2. So we have a whole bunch of lines that are parallel, that are crossing at different intercepts, and it all depends on what that c value is. And we'd have to know an ordered pair in order to get that c value. So moving along here, we're asked to take the antiderivative. Now we're going to get into a little bit more formal notation. I didn't give you really any notation in the previous slide, but the formal notation of this, remember, so this was my derivative function, so this is y prime is equal to 3x. And so a little more formal notation is that when we did dy over dx is another way to say 3x. And so then we did differentials, which gave us something that looked like this. And this is that little bit of change that's a little bit different when we're doing our tangent line approximation. And so then we're going to use our indefinite integral sign, which looks like a little s, and we'll talk more about what that means in a little bit here. And when I do the antiderivative of dy, that gives me y. And then over here we're going to write the antiderivative of 3x dx. And so this is going to be the more formal way we're going to see it. So when we do the antiderivative of this original function here, we get something that looks like this. The antiderivative of dy is there's a 1 here. And so when we do the antiderivative of it, what we talked about, we end up picking up a variable, which happens to be y. The dy and the dx are telling us what variables we're integrating about. And so those are the ones that are going to raise powers and stuff like that. So now if I do the antiderivative of 3x dx, well, I could, knowing that there's a constant, that 3 is a constant, I could move it outside and do the antiderivative of x, which might be a little bit easier. And so I would end up with y equaling 3 times the antiderivative of x is, well, remember before when we were doing the power rule, that we would take the power, multiply it out front, and then reduce the power by 1. Well, we're going backwards, so we got to do everything in reverse. Well, we're going to raise our x power by 1, but instead of multiplying by the power, we're going to do the opposite. We're going to divide by that new power. And so we get something that looks like this. So we have 3x squared over 2. Now think about it. If I was to do the derivative on this, the 2 gets multiplied by the 3, which gives us 6, and then we divide it by 2, we get back to the 3 that we originally started with. So that should make sense. Now don't forget that I have to come up with some constant, because remember, this is a family of functions. We don't know exactly what ordered pair it's going through, and by the end of this we'll talk about how to find that c value. So this is the antiderivative of 3x, is this function right here. And so as we move along, sometimes it might be better for us to rewrite these before we do the antiderivative. So I might want to rewrite this one as x to the negative 3 dx. When I integrate it, I raise the power of x by 1, so that becomes negative 2, and I divide by that new power and add on a constant. So then to simplify this, I might get something like 1 over negative 2x squared plus c. That would be something that I would look at. Maybe the negative would be on top or something like that. But so sometimes it's best to rewrite these things before we integrate. So like to rewrite this next one, I might try x to the 1/2 dx. And so then when I'm going backwards, I'm going to add a power to this. So I'm going to add 1, which gives me x to the 3/2. And I got to divide by 3/2 and then add c on. Well, when I divide by 3/2, isn't that just dividing by a fraction means that I multiply by the flip of the fraction, so I end up with 2/3 x to the 3/2 plus c. So I get something that looks like that. And then the tricky ones are when we get to sine and cosine. If I'm rewriting this, I might rewrite it like this, bring out the 2 because it's a constant multiple, oops, and then this is sine x dx. That would probably be one way I'd rewrite it. Then I have to remember, what did I differentiate to get sine? Well, I differentiated cosine would get me a negative sine. So when I anti-differentiate sine, I'm going to get a negative cosine. So when I integrate it, I'm going to get negative cosine x. And then don't forget your constant. And then a little simplification would be something like this. And so that's really what we're talking about when we're rewriting these, and it's sometimes best practice to do that on a few of these. So then here are some other options out here. Well, if I didn't show you this part, if I said the integral of dx is the same as 1 dx, and when I integrate this, since there's nothing there, there's just a 1 there, to get that slope I had to have a power of x, and now I'm just going to add on c. So there is my antiderivative integrating this. This guy here could be broken into 2 different terms if you like. And so then I am going to anti-differentiate this, and that means I raise it by a power and divide by that new power, and raise this guy by a power of x, which will give me 2x. If I divide it by 1, it doesn't really get me much, and so I'd get something that looks like that. Down here, I could break it apart if I wanted. That might be easier, or I could just go through and just know that it's kind of like the distributive property, and I got to do each part separately, since this is a polynomial just like the one up above, and I can just integrate each part. So if I raise this by a power, I'm going to get 3x to the 5th, divide by that new power, and here I'm going to raise this one by a power, and it'd be 5x to the 3rd, divided by 3, and then same thing, raise the x by a power, and divide by that new power, and then don't forget your constant. And so I'm not going to try to get a common denominator or anything like that, but this is the simplification of this. Moving on to the next one, well, in this case, it might be best to rewrite this, and don't forget, since I'm dividing by a single term, I can basically divide both of these guys by that single term and rewrite this. So I'm going to rewrite this integral, since this was x to the 1 over, I'm going to rewrite it like this. Since it's adding on top and just nothing on the bottom, I'm going to do each part separately. And even better, if I say this is a power of 1, this is a power of a half, we subtract our exponents. I could call this x to the 1/2, and then here this would be x to the negative 1/2. And so then I can go ahead and integrate this. And when I integrate that, I end up raising a power and dividing by that new power. So it's going to be x to the 3/2 divided by 3/2. Here I'm going to add 1, which will take it to x to the 1/2 and divide by that 1/2. And then don't forget your constant. And so just a quick little simplification is that I'm going to flip these fractions over. So finally I'm going to end up with 2/3 x to the 3/2 plus 2x to the 1/2 plus c is what I got. And now with all of these, if you want to check and make sure that you have them simplified as best as possible, you might want to go through and differentiate them differentiate them to go back to see if you get back to where you started from. It's always kind of a good practice. It's a forward and reverse type thing. You could always check and make sure you're getting close to the correct answer on these, and it'd be a good way, the one chance you get to actually check your answers. So then, of course, we got to have a trig function one, and so I'm probably going to rewrite this one to make it a little bit easier. I'm actually going to get it out of sine and cosine form. So I might write this as something like sine of x over cosine times 1 over cosine of x dx. Well, sine over cosine, I believe, is tangent, and 1 over cosine is secant. So I could rewrite this as secant x tangent x dx. Now, when I have to do an antidifferentiation of a trig function, I have to think back to what did I differentiate to get to this point. And I have to think, well, what did I differentiate to get to secant tangent? And if I remember my rules from differentiation, that secant tangent came about when I differentiated secant. So this becomes secant x, and it's just plus a constant. So there's my final answer for this problem. So then we might want to talk about finding a particular solution to a function. And so this is we're going to find the general solution, and then we're going to find the particular solution that follows these conditions. So first thing, a general solution, remember, has the value of c in it, so we'll do that. And then when it says a particular solution, that means we're going to find the value of c using those points. So we do everything we do what we've been doing, and then we will go ahead and find what that c value is. So if I want f of x, well, f of x comes about the antidifferentiation of the original function, so I get something like this, or this. Then I'm probably going to rewrite this, which basically means I'm going to write it like this, just make it easier on myself. So when I do the antidifferentiation, I'm going to raise the power by 1, which means it's x to the negative 1 now, and I'm going to divide by that new power and add on a constant. So my function, my position function, this was a velocity function, 1 over x squared. Now my position function is that I have negative 1 over x plus c. So there's my position function. So this is a family of functions. But I want the function to go through the point 1, 0. So that means that I know what my y value is. My y value is 0 when my x value is 1. So I can go ahead and plug these guys in. So this is the, I'll circle this, this is the general solution up here. General solution. And then if I plug in my x and y into this function, well, 0 is going to equal negative 1 over 1 plus c. Well, that means that c is 1, and so my particular solution is that f of x will equal negative 1 over x plus 1. And that is the particular solution I'm looking for when I solve this problem. And then last but not least, we have an object being thrown in the air. A ball is being thrown upward with an initial velocity of 64 feet per second from the initial height of 80 feet. So find the position function given that the height s and giving the height s as a function of t. And then when does the ball hit the ground? So first thing that we know is that when we know our initial height is 80 feet. So we're off the ground, we're throwing the ball off a building. So we're something like this. We're throwing a ball 80 feet off the air, and it's probably going to do something like this. This is 80 feet, and the ground's probably down here, so we want the ball to hit the ground. And so that's what we want to know, is when the ball is down there eventually. So we're 80 feet off the ground. We know that the initial velocity at time 0 is 64. And so we should know, since we're dealing with feet per second, that the acceleration due to gravity, is negative 32 feet per second. And so now I'm going to work backwards. If I take the antidifferentiation of negative 32, that will give me the velocity. So when I do that, s prime of t is going to be negative 32x plus some constant. Well, do we need to find that constant? We probably should. We know that the initial velocity, and I should be using t here, but we know our initial velocity when t is 0, we get 64. So we could say, oh, well, I'm going to use this value over here and say, oh, well, 64 has to equal negative 32 times 0 plus c. So c is 64. So my velocity function, my particular velocity function for this problem is s prime of t will equal negative 32t plus 64. Well, if I anti-differentiate this one more time, if I take the velocity function that I got and anti-differentiate it one more time, that will give me the position function that I'm looking for. So I anti-differentiate it, that would give me s of t. So I get to anti-differentiate negative 32t plus 64. And by doing that, s of t will give me, well, negative 32t squared divided by 2 plus 64t divided by 1 plus c. And so with that being my setup, then if I divide negative 32 by 2, I get negative 16. So s of t is negative 16t squared plus 64t plus c. Well, I need to know the actual function, but I know the initial condition is that I was 80 feet off the ground. So if I put in 80 for s of t and 0 for t, I will get that c is 80. So the position function that I'm looking for, it would be s of t is negative 16t squared plus 64t plus 80. So there's my position function. But we want to know when the ball hits the ground. So how do we find out when the ball hits the ground? Well, we would do that by saying what is the height of the ball when it hits the ground? That's position. The position of the ball is 0 when it hits the ground. There's 0 down there. So I'm going to take the position function that I worked so hard to get and set it equal to 0. So 0, when the ball's on the ground, is going to be negative 16t squared plus 64t plus 80. Now, I believe if I factor out a negative 16 out of this problem, I will get something like t squared minus 4t, and I believe that'll be minus 5, which is factorable, which gives me t minus 5 and t plus 1. Well, 16 really divides out, becomes 0, so I have t minus 5 or t minus 5 equals 0, or t plus 1 equals 0. So t is either negative 1 or t is 5. Well, I'm guessing that t is 5 would make the most sense because the ball is moving forward. As time moves along, we're going to go 5 seconds to hit the ground. And if you look, if I went backwards, I'm guessing they're saying that to drop that 80 would take another negative 1 second. We'd have to go back 1 second to get the ball to drop that far. But we're not doing that, so we never use negative time. And so our final answer is when the ball hits the ground is 5 seconds after we threw it. And so if you have any questions on any of these examples, please bring them to class, and please come prepared.